All right, everyone, so I'm Ashley, and I'd like to talk to you about a new choreographic programming language that I developed together with my advisor, Ethan Cecchetti, and our collaborator, Andrew Hirsch. Both Andrew and I will be here to answer any questions you might have offline after my talk. So we're interested in concurrent programming languages, and if you've ever tried building a concurrent system that doesn't immediately break, you might know just how hard that can be. In concurrent programming, you typically have a program for each process in your system, like Alice or Bob. To ensure that nothing goes wrong, you need to both ensure that Alice and Bob's programs don't have any errors, and that all communication between those two processes goes as expected, which means that no one sends an unexpected message, and no one waits for a message which never arrives. Well, for two processes, this may not seem bad. As you add more and more processes to your system, you have to add a new program for each of those processes and verify the communication between all pairs of processes. And this just makes our developers' heads spin. You can't manage all these programs and all this communication that happens. So concurrent programming is hard. And this isn't even to mention the other sources of bugs in concurrent programs, like data races. But fortunately, there is a solution. And that solution is choreographies. So choreographies make concurrent programming easy. So choreographic programming is an emerging paradigm for concurrent programming that seeks to simplify concurrent software development while yielding strong formal guarantees. So in the choreographic paradigm, you write a single top-level program called a choreography that specifies the actions of all participants in the system, regardless of how many participants there are. We then have a compilation procedure called endpoint projection, which extracts out the actions of every single participant in that system, yielding a system of programs that can be then executed concurrently. So besides simplifying that software development, choreographies also have a property called deadlock freedom by design, which means that if you can prove that the choreography is safe, which is typically done by means of a lightweight type system, then you can transfer this guarantee to the concurrent system created by endpoint projection. And this concurrent system will be deadlock-free, meaning there will be no deadlocks in the system, and it won't crash for that reason or any other reason. So to illustrate some details about how choreographies work and to motivate our work, I'd like to talk about how a programmer can implement a system in which Alice buys a book in collaboration with a few other processes. So the book that Alice wants to buy is called A Death in Venice by Thomas Mann. So to determine which of Bob and Charlie she wants to buy this book from, she's first going to tell Marty which book she wants to buy. Marty stores a list of all the prices and availability of these books, and Marty will send this data back to Alice. So we could let Alice choose to decide her vendor based on any criteria we want, such as preferring a local business. But for simplicity, let's just have her choose the cheapest vendor, which in this case is Charlie. So importantly, this procedure was dynamic. Alice only learned this information at runtime. So if there's a different execution environment of this program where the prices might have been different, Alice's decision might differ. And this feature is a key, this ability is a key feature of our work. So then lastly, to complete this transaction, Alice sends the name of the book as well as the purchase price to the chosen vendor, Charlie, and Charlie can send back the book, and then everyone is satisfied. So as I mentioned, the key component of that process that we want to work on in our work is to enable choreographies to dynamically select processes. So prior work technically has the ability to implement this functionality, but it was never a major focus of prior work, so it's up to the programmer to implement this functionality in an ad hoc manner using other features. In our work, in contrast, we enable dynamic process selection in a programmer-friendly manner by adding new language features, which increase modularity and decrease the chance for errors. So let me show you how this book buying example can be written using prior work. So the nice thing about choreographies is they look very close to normal single-threaded applications, except you sometimes have some extra information to denote which of the processes in your system will perform each action. So here we allow Alice to choose a vendor by prefixing the name of this function called choose_vendor with an A followed by a period. So this function returns a string representing the chosen vendor. So we're going to branch based on that value. So in this first branch, we handle when Bob is chosen. The code that this case executes calls this transaction function with the arguments Alice and Bob. This transaction function is process polymorphic. It abstracts over the processes in this function, which is a feature of prior work. This means we only need to write this transaction function once and just call it using different arguments in each branch. But if we want to add another vendor to our system, say Dan or Aaron, we need to add another branch to our case expression and change the arguments to this transaction function. 4 vendors isn't super realistic. We have to add a lot more vendors for a more realistic scenario. We have to add another case of our case expression for each of these vendors. But this isn't very modular. This isn't a very good idea, because if you zoom in here, you can see there's actually a mistake. When Oliver was the selected vendor, the sale mistakenly went to James. And this isn't a very good thing to happen. In fact, this is a real mistake I made when typing up this example. So writing so many cases is very clearly unsustainable and can lead to programmer error. And this, again, makes our developers' head spin. So how can we fix these problems? So our main observation is that if we can treat the name of the selected vendor like any other value and bind it to a variable, then our programmer can write this book vendor example in a simple and modular manner. So that is, our solution specifically is to treat these process names as first-class values. So just like before in this code, Alice first dynamically selects a process by calling this choose_vendor function, producing this time a first-class process name. However, in our new language, there's no need to branch based on the value that selected vendor takes. And this is because of a key contribution of our new language called a type-let expression. So this is a new form of let expression, which binds that vendor to the process variable L. So the body of this let expression is nearly identical to in the previous implementation, but we're replacing the specific vendor, like Bob or Charlie, with that process variable L. So this both eliminates the duplicate code, which appeared in the branches of the previous example, and allows the programmer to reduce the chance for errors by writing it once and for all, regardless of how many vendors are in the system. But you say, this is a let expression. This is kind of simple. Are you really going to stand up here and tell us how let expressions work for the next 5 minutes? And that is kind of what I'm going to do. But it's not that easy. If this solution works, well, why didn't previous languages implement it? Well, it's not that they didn't know what let expressions are, didn't think to add in let expressions to their language. First-class process names are actually quite complicated. So let me show you how our language manages to safely implement this feature. So firstly, we need to be a bit careful about the sort of things in this program, because when Alice chooses this vendor, this is something like a string, an expression, but this process variable L is actually at the level of types. So to give this let expression a sensible semantics, we need to have a way to convert expressions into types. And we allow this in our language by letting the user configure the runtime to define this conversion function. Another subtle point is that if you ever see in programming languages an arrow pointing from expressions to types, you should immediately think of type dependency. And dependent types aren't necessarily bad, per se. They can just make your type system extremely complicated or even undecidable. So in our language, we would really like to avoid type dependency whenever possible. So to see how we might unintentionally introduce dependent types, in this example, if the chosen vendor returns their street address, in one case, when Bob is chosen, that results in a string at B, or Bob. The other case, it results in a string at Charlie. So then what type should we assign to the entire let expression? Well, it depends on what value L resolves to. So our language solution to this is basically just to ignore this. We say this isn't allowed in a language. Well, we don't exactly ignore it. So to be more precise, what we say is that we look at the type of this expression where the variable L is in scope, look at the type of it, and say, if it depends on L, this is not allowed in our language. So this example is not allowed because a string at L clearly depends on L. So we don't allow such a let expression to type check in our language. In contrast, that earlier actual example of our book vendor returns a book at Alice, which does not depend on the chosen vendor L. So this entire let expression type checks in our language, and it produces a book at Alice. So by imposing this mild form of restriction on how this let expression can be used, we can completely avoid dependent types while still allowing forms of dynamic process selection. So another small problem that comes up in our language is called the knowledge of choice problem. And this involves a scenario where Alice selects a dynamic process, but Bob and Charlie don't necessarily know who was selected. Charlie doesn't know whether to wait for a message from Bob and from Alice, and neither does Bob. So in our language, we enforce that this message is sent to both Bob and Charlie, the relevant processes, before that transaction can occur. Once that information is conveyed to Bob and Charlie, the transaction can proceed as normal, where Alice will then send the message and money to Charlie, and Charlie will send back the book. If a different vendor was selected, the name of our language implies that we can quickly change the selected vendor from Charlie to Bob. So in conclusion, we developed a language called the Choreographic Quick Change Calculus, or Lambda QC. We added new first-class process names, as well as a type of let expression to handle those first-class process names. We used existing features from previous choreographic languages, like process polymorphism and multiply located values. We have an endpoint projection compilation procedure to compile these choreographic programs into one for each process in the system, and all of our work is verified in Rocq. Thank you, and now I can take any questions.
Thank you. Unfortunately, we don't have time for questions.